Well, hello and welcome again to our journey into algebra and number theory, and in this section we're going to look at quadratic reciprocity. So in earlier sections we looked at some nonlinear congruence equations modulo m, and we're going to narrow our viewpoint a little by just considering quadratic equations modulo m. So a simple example here, we want to look at x squared plus 4x plus 2 is congruent to 0 mod 7. We can complete the square on this in the usual way, so we take half the coefficient here, right, this is x plus 2 all squared, and we have to put we get an extra 4, so I need to pick up a 2 on the other side to make it balance, and so we end up with this. The question now becomes, are there elements in Z7 whose square is 2? So can we find an object whose square is 2 in mod 7? And trial and error says we can, and in fact of course 3 squared is 2 and 4 squared is 2 mod 7. So that means this x plus 2 is 3 or x plus 2 is 4, and I get x is 1 or 2 mod 7. Well, this is an interesting question then, and how do I know that these are the only solutions? Well, we saw before, because 7 is prime, we know that this polynomial will have at most 2 solutions, and we've got 2. But we can see from this example, the key question is, can we solve x squared is a, so for some given a, and some given modulus, can we solve x squared is congruent to a modulo m? Now we're going to further restrict the problem by supposing that this m is a prime number, and just look at squares modulo a prime. Well, first little theorem here, that if p is an odd prime and a and p are relatively prime, that's their GCD is 1, then x squared is congruent to a mod p has exactly 2 solutions, or it's got no solutions. Well, obviously if x is a solution, so is minus x. Moreover, if these happen to be the same modulo p, then that says 2x is 0 mod p, so x is 0 mod p. But that's out of the question, because we chose our a that had the GCD of these two is not 1 in that case. So conversely, we know that this, because p is a prime, we know that this has at most 2 solutions. Now the result is not necessarily true if p is not prime. A classic example of this is x squared congruent to 1 mod 8 has got 4 solutions, which comes as a bit of a shock, given it's only a quadratic, but modulo 8 there are 4 non-congruent solutions. Well, an important and very special case of this congruence is when is minus 1 a square mod p? And you can experiment a little bit to this, and you find that the equation does have solutions if p is 5 or 13 or 17 or 29, but no solution if it's 3, 7, 11, 19. And if you look carefully at these numbers, especially divide them by 4, you'll see that all these numbers are 1 mod 4 primes, and all these numbers are 3 mod 4 primes. And this is, we see here that the primes bifurcate into these two classes, the 1 mod 4s and the 3 mod 4s. So our second theorem says that the congruence x squared is congruent to minus 1 mod p, where p is prime, has solutions, in fact 2 solutions, if and only if, well, p could be 2, a little bit of noise, or p is 1 modulo 4. So in other words, minus 1 is a square mod p for p an odd prime, if and only if p is a 1 mod 4 prime. The case p equals 2 is a bit of noise at the beginning, that's trivial, so I'm going to suppose p is not 2, and we're going to suppose there is an x such that x squared is minus 1 mod p, and we want to show that p is 1 mod 4. Well, we can square both sides of this. I get x to the 4th is 1 mod p, and that means this x has order 4. Can't have order 2, but when you raise it to the fourth power you get 1, so that means x has order 4, and that means 4 divides phi of p, as we've seen before. This divides the order of the group, and that said, but phi of p is p minus 1, so that means p minus 1 is some multiple of 4, that is, p is congruent to 1 mod 4. Now for the converse, to show that if p is 1 mod 4, then there is a solution, we're actually explicitly going to write down the square root of minus 1 modulo p in the case where p is a 1 mod 4 prime, and we do this by using Wilson's theorem, which you may recall says that p minus 1 factorial, that is this quantity, all the numbers multiplied from 1 up to p minus 1, is congruent to minus 1 mod p, which we did in a previous section. Now what you do is here you write the numbers down 1, 2, 3 and you stop halfway, that's p minus 1 over 2. The next number in the list is p plus 1 over 2, all the way up to p minus 1. And now you read these numbers backwards, so p minus 1 is congruent to 1, to minus 1 I should say, p minus 2 is congruent to minus 2, and p plus 1 over 2 is congruent to minus this number. So that's what we've written here, p minus 1 is minus 1 mod p and so on. And that means we can then replace all of these numbers with minus signs. Now we just count the number of minus signs here, and we're going to get p minus 1 over 2 minus signs. And so we're going to get 1 times 2 up to p minus 1 over 2 all squared, and I'm going to get p minus 1 over 2 minus signs. Now, that's still, we know that that's congruent to minus 1 mod p. Now, if p is 1 mod 4, then that means p is 1 plus a multiple of 4, so p minus 1 over 2 is even, and minus 1 to an even power is 1. That means then we have p minus 1 over 2 factorial squared is minus 1, and that gives me an explicit solution to x squared is minus 1 mod p in the case of p 1 mod 4. So this thing here, p minus 1 over 2 factorial, is the square root of minus 1 mod p in the case when p is 1 mod 4. And that's how we can finish it. So we've explicitly constructed a solution to x squared is minus 1 mod p. So simple example here, we want to solve x squared is minus 1 mod 17. 17 is a 1 mod 4 prime, and the solutions then are plus or minus 17 minus 1 over 2 factorial, which is 8 factorial, and from a calculator you can show that 8 factorial is 13 mod 17. And indeed you can check, if you do 13 squared 169, and if you add 1 to that you get 170, which is obviously 0 mod 17. Note however the converse is false, that is, if x squared is congruent to minus 1 mod p has a solution, then p is not necessarily prime. So one has to be very careful with these things. So this can have a solution without p necessarily being prime. For example, if we take 2 to the 16 squared is congruent to minus 1 modulo this number, but this number 2 to the 32 plus 1 is one of the Fermat primes, one of the Fermat numbers. It's 2 to the 2 to the 5th plus 1, and of course that's the one you may know factorizes. So 2 to the 32 plus 1 happens to factorize into 641b 6700417. You may recall that Fermat believed incorrectly that all numbers of the form 2 to the 2 to the n plus 1 were prime, and Euler proved that was false, and this was the example he gave, in fact. So it's not prime. So I have to be careful with these things. So if x squared congruent to a mod p has a solution, now I'm going to introduce some terminology here. We're going to call a quadratic residue. I just call it a square but it's called a quadratic residue modulo P, or QR for short. If there's no solution, then we say that A is a quadratic non-residue modulo P. In other words, A is a quadratic residue modulo P if and only if it is a square, the square of something, in ZP. 0 is usually excluded. So here as an example, if we take Z11 star, that is all the numbers from 1 up to 10, and we take their squares, modulo 11, that's what you get. And just enjoy the table. You'll see, of course, that it goes inwards because this is x and minus x being squared, and therefore the quadratic residues are going to be 1, 4, 9, 5 and 3. That means the quadratic non-residues are the numbers in Z11 star that are not in this list at the bottom, that is 2, 6, 7, 8 and 10. Now, as you might gather, it's pretty obvious that exactly half of the non-zero elements in Z11 are quadratic residues and half are non-residues. And this is almost obvious from the fact that x and minus x are going to square to the same thing. But I've done a little proof here because it actually slightly more complicated than it needs to be, but it does have some interesting little ideas in it which are very useful for other things. So the proof of this might be obvious, but I'm going to do a slightly more sophisticated proof here. So if P is an odd prime, then exactly half of the numbers are squares. They're quadratic residues mod P. And the proof of this goes as follows. We're going to use the idea of primitive roots because we're working modulo P, and we've seen before that ZP always has a primitive root. In fact, 5P minus 1 primitive roots. So if G is a primitive root modulo P, then that means we can generate ZP star, or UP, by simply taking all the powers of G. These are going to be distinct, and they will generate for you U sub P or ZP star. So clearly all the even powers of G are going to be squares, so G squared, G to the fourth and so on. We only need to show that the odd powers are not squares. So suppose we take an odd power of our primitive root, and suppose that was the square of something, and of course something can be written as G to the S, and so suppose that's the square of that, modulo P for some integer S. Well, we can rearrange this equation as G to the 2k minus S plus 1, congruent to 1 modulo P. You see why this step is valid, because G will have an inverse, and the inverse of G to the S is G to the minus S, or multiplying both sides by that. Now, that tells me then that this G then, when I raise it to this power, I get 1, but we know that G has order P minus 1, which is even. And the trouble is this number here is odd, and so an even number cannot divide an odd number, which is odd. And that means that the odd powers of G cannot be squares. Hence the only squares are these ones, and there are precisely P minus 1 over 2 of them. So example here, 2 is a primitive root modulo 11. So if we want to write down all the squares, we simply have to work out the even powers of 2. That's 2 squared, 2 to the fourth and so on. And we get 4, 5, 9, 3, 1, which is what we saw before. Exactly as we found in the earlier example. Now, we would like, this works nicely for very small numbers, but we want to deal with much bigger numbers, and so we're going to need a little bit more sophisticated test for whether something's a square, and that's going to bring us to Euler's criterion, which is the next part of the story in quadratic residues, which we'll do in the next recording.